Hi everyone. Right, so in today's video I just want to do a quick review of a possible question, quite a popular question that comes up in calculus, right? And this is what they call graph interpretation, right? So this type of question does throw students off a little bit, so I'm going to try and just give you a little bit of clarification, okay? So over here, right, you are given information about your derivative function, right? So in other words, you're given information about f prime of x, okay? And then you are asked to answer questions about the original function f of x, right? And some kids freak out saying that they don't have enough information to actually answer questions about f of x because they don't know what it looks like and all of that, but you actually do have enough information, right? So we're going to see that in just a few moments, okay? Right, so the first thing that you should be recognizing, right, is that the fact that your first derivative, okay, is a quadratic function, right? Then we know that our original function, okay, is a cubic function. Right? So up until this point, the way that you've been really working with the quadratic function is either in inequalities, right, when you're finding where you have x values greater than or equal to 0 or things like that, or just basically just sketching the quadratic function and answering questions about it, and that was it, right? So now that you've come to the section of calculus, right, you need to have a little bit more of an appreciation of the quadratic function, right? And you need to appreciate it at the level that this function, right, as it's sketched, right, is no longer just a sketch of a parabola, right? This is giving you information, right, about the gradient of the tangent line at any given point on your original function f of x, okay? And how does this simple parabola do that? Well, it does that simply by the points on the parabola. Okay, so every single point on this parabola, let's take, for example, this point over here, right? Every single point has a defining x value. Okay, so let's say this x value is 4/5, which is a point 0.8. Okay, its corresponding y value, right, is not f of is not just f of 4/5, but f prime of 4/5. Okay, so in other words, this coordinate point, right, is giving you the slope of the tangent line, okay, at x is equals to 4/5 on the function f of x. Okay, do you see that, right? So technically, your y-axis over here is f prime of x, right, is equals to y, right? So what you can understand this graph to be is that every single y coordinate on this graph, right, is equals to the slope, all right, of the tangent line of a tangent line on f of x. Right, and we also looked at this idea when we were talking about our derivative number line. Okay, so remember we came across the derivative number line when we were sketching our cubic functions. We also came across it when we were doing our optimization problems. Okay, and the way that we use the derivative number line is that we put down our critical values, right? And the critical values were when f prime of x is equals to 0, right? And you can see that f prime of x is equals to 0 over here at the x-intercepts, right? So at the x-intercepts, you have f prime of x, right, equal to 0. Right, so we would put that on the derivative number line. So that would be 1 and 3 as your critical values, right? And what the derivative number line would give us, right, by using test values within each interval, okay, is either a positive or a negative sign, right? And when we got a positive sign, that told us that our original function is increasing for that interval, right? And when we got a negative sign, it told us that our original function is decreasing for that interval. Right, so how does this information on the parabola, okay, transfer to a derivative number line? Well, you can see that when you look at x values less than 1, right, if prime of x, right, which is these y values over here, okay, all of those values are positive. Okay, can you see that, right? Okay, so for x values less than 1, right, okay, you can see that your f prime of x is above the x-axis, right? In other words, it has positive values, right? So on your number line, what that would look like is that you would get a positive sign for this interval. Okay, and then when you go to the x values in between 1 and 3, right, for these x values in between 1 and 3, okay, you can see that the function is below the x-axis. In other words, it always has negative f prime of x values, right? So negative y values, right? So on your number line, that would correspond to a negative sign. Okay. And then also again, lastly, for x values greater than 3, okay, you can see that for x values greater than 3, right, your function goes above the x values again, right? In other words, it has positive, okay, f prime of x values, right? So on your number line, that would correspond to a positive sign. Okay, so we were able to then deduce from this number line, okay, that for the fact that we are moving from a positive gradient, right, to a negative gradient means that the original function f of x is increasing for this interval, then it decreases, right, and then it increases again, right? So that means that you would have a local max over here at x is equals to 1, right? So you would have a local maximum at x is equals to 1, and you would have a local minimum, right, at x is equals to 3. Okay. Right, so basically what I'm trying to say is that the derivative number line, okay, can be represented graphically by using the derivative function, which is a quadratic function for a cubic function, right? Now, when you look at the first question, right, so they ask you to find the x coordinate, right, at the point of inflection of f, right? So now f is our original function, which is the cubic function, okay? Now, we know that for a point of inflection, right, this would occur when f double prime, right, which is the second derivative of x, right, when that was equals to 0. Okay. Now, notice that the second derivative of our original function f of x is the first derivative of our f prime of x function. Okay. So you can sketch that as well, right, because the second derivative function is doing exactly the same thing as what this f prime of x function is doing. It's recording the slope of the tangent lines along the original function. Okay. So I'm just going to clean up a little bit. Okay, so if we quickly had to sketch f double prime of x, right, you can see that the simplest point to sketch is this point over here at the turning point, because we know that at that point, okay, the gradient of the tangent line is equals to 0. Okay, so f double prime of x would have a x-intercept at that point. Okay, then for x values less than, right, this specific x value here at this point in red, okay, what is the second derivative function capturing? It's capturing the slope of tangent lines along this f prime function, right, so along this parabola. Okay, and you can see even when we draw a tangent line to this point 4/5, that tangent line is negative. Okay, so all that means is that for the interval less than this x value here in red, okay, our original function, which in this case is the parabola, right, that original function is decreasing. Okay, and then for x values greater than this x value here in red, right, remember what are we capturing? We're capturing the value of the gradient of the tangent line to this graph, right? And you can see that when we draw a tangent line, maybe to this point over here, okay, that tangent line is sloping upwards. In other words, it's a positive gradient, right? So then the function for this interval would be above the x-axis. Right, so we would have positive gradients, right? And for x values less than this point, we would have negative gradients. Okay, and it's as simple as that. Okay, so basically our parabola, right, is a graphical representation of f prime of x, right? And this straight line function, which I didn't draw very straight, but it's a straight line function, that is the graphical representation of f double prime of x. Right, so you can see that the correlation that occurs over here is that at the x value at your turning point, right, always becomes a x-intercept. Okay, right, so we basically can find the x-coordinate at the point of inflection, right, because that is just the midpoint, right, between these two x-intercepts of the parabola. Okay, so now we know how to find a midpoint, right? We don't need the corresponding y value, so we're just going to focus on the x value, right? So that's going to be this distance, right, the horizontal distance, right, which is going to be 1 plus 3. Okay, so the x value at the turning point, okay, is equals to the x value at the point of inflection. Okay, so that is 1 plus 3, okay, divided by 2. And 1, 3 is 4. Divide that by 2. We're going to have an x-coordinate of 2. Right. So at an x-coordinate of 2, right, our original function f of x has a point of inflection, right, and the second derivative function has a turning point. Okay. Right. So for b, right, they ask us to find the x values for which f is increasing. Okay. We've already done that, okay, by looking also at the derivative number line. Okay, so we know that f, okay, is increasing whenever f prime of x, right, is positive, or the way we write it in math, sometimes we talk about it being greater than 0. Okay, so you can see that if prime of x is greater than 0, or in other words above, right, the x-axis, whenever, okay, x is less than 1, okay, or when x is greater than 3. Okay, And if you wanted to write this in interval notation, you could write it as x, an element, right, of negative infinity to 1 union 3 to positive infinity. Right. So then a similar question, okay, is to find the x values for which f is decreasing. Okay. So for this question, it's basically the opposite of what we just did above, right? F is decreasing whenever f prime of x is less than 0. Okay. And we saw that on the derivative number line, okay, that f prime of x is negative between 1 and 3, okay. And if you didn't draw the derivative number line, you also get the same information from the graph of f prime of x, right? Because f prime of x less than 0 basically talks about where f prime of x is below the x-axis, right? So in other words, it has negative, okay, y values, right? So that's just simply when x is greater than 1, right, but less than 3. Okay, and we don't include 1 and 3, okay, because at that point f prime of x is equals to 0, right? So those two critical points or x-intercepts, those are not included, right? Again, if you wanted to write this in interval notation, it would be x an element, right, of open bracket, because it's not included, 1, 3. Right. Okay, so lastly, now ask you to sketch f of x, right? So the sketch of f of x is simply just you capturing the intervals of increase and decrease, right? So I'm going to sketch it in green, right, on top of this, right? But let's just clean this up a little bit first. Okay, so when it comes to sketching f of x, right, we are basically just capturing, right, these intervals of increase and decrease, right? So we know that importantly, we need to just pay attention to the fact that at x is equals to 1 and at x equals to 3, right, we have our stationary points because that's where f prime of x is equals to 0, right? And then we know that our first interval, right, where we have x less than 1, okay, the function f is increasing, okay. So we would come in from the left hand side, right, and we would go up, right? So what does that correspond to? It corresponds to the fact that as you are increasing in x values, right, you are increasing in y values, okay. So you come up, right, and it doesn't really matter how high you go, right, you just need to capture the fact that at this x value of 1, you have a stationary point, right. Then we need to capture this interval, right, that between 1 and 3, f is decreasing, right, so it's going to come back down, right, and you're going to have your second stationary point here at 3, right. And then lastly, this interval for x greater than 3, right, again your function goes back up and it starts increasing again. Okay, so now sketched in green is our original function f of x, right, and you can see that it is a cubic function, right, and we talked about this throughout the series of these videos, right, that when you have a cubic function, you take the derivative of that, you get a quadratic function, and when you have a quadratic function, you take the derivative of that, you have a linear function, right. So notice that when we sketched, right, so in answering D, right, when we sketched f of x, right, we were not worried about where does f of x have x-intercepts, right, or where does f of x have a y-intercept, right, because we're not given information that helps us to answer that, right. The only information that we were given is the location of our stationary points, right, and they give that information to us by the fact that at these points, right, f prime of x is equals to 0, right? And we know that when we set f prime of x equals to 0, we are finding the x value at the stationary point of our cubic function, right? So that's how they give us that information. Do you see how graphs are so powerful? The examiner doesn't have to write it down in words. They just give it to you in graphical representation, and a picture speaks 1,000 words, as cliche as that sounds. Okay, and from that we will also be able to deduce that with the same logic, right, when you consider the quadratic function as a function itself, right, a quadratic function, we call this point a turning point, but you can also call it the stationary point, right? For the quadratic function at that stationary point, its derivative, okay, function, which is f double prime of x, right, would also have a gradient of 0, right, and thus at its turning point as well, its derivative function also has an x-intercept, right? So then from that you are able to sketch basically the original function f of x, right, the derivative function, and the second derivative function. Okay, so notice that with this original function f of x, you can move it up or down, right? So that's called translation, right? So you could have drawn it a little bit higher like this, maybe. Right, where you translate the graph upwards, right? Or you could have drawn it like this, where you translate the graph downwards, right? But basically, all those shapes, right, would be correct because you are capturing, right, where you have your stationary points, and you're also capturing your intervals of increase and decrease, right? So how you get marks for sketching f of x is firstly the shape, right? So firstly the shape here would have to be correct. So in other words, it's starting from the left hand side and it increases towards 1, right, then decreases, then increases again. Okay, you would get a mark for the shape of the graph. You would get a mark for correctly assigning the proper stationary point. The fact that at x is equals to 1, you have a local maximum, and at x is equals to 3, you have a local minimum, right? And then also correctly representing the intervals of increase and decreasing. So for x values less than 1, you are increasing. Between 1 and 3, you are decreasing. And for x values greater than 3, you are increasing again. Okay, so you didn't draw it the other way around, right? And that's what you would get marks for. Such questions are usually 4 or 5 marks in exams, as I've seen so far. Okay, right, so that is essentially the important part. Capture the shape, capture the intervals of increase and decrease, and also capture the correct form of your, or let me use proper language, capture the nature of your stationary point, right? So is it a local maximum or a local minimum? Okay, I hope that helped, and I'll see you guys next time.